We're good? Hi, everyone, and welcome to our AI Salon. We have a very special AI Salon for you guys today. My name is Jorge Cueto, and I'm one of the organizers for the AI Salon series. If you're not familiar with AI Salon, we're a roughly bi-weekly series in which we come together on Fridays to discuss high-level topics in machine learning and AI with the goal of helping us to step away from our day-to-day research and our studies and look at how the work we're doing on a day-to-day basis fits into the bigger picture of society. And these events are modeled after Enlightenment-era salons, so we don't use any electronics, and we don't use the whiteboard. It's all an open discussion. So once we actually move to the discussion part, we'll have a microphone here that Andre will be holding. And so if you have any questions or comments, please make your way to the side to ask your question. And this is definitely a conversation. So please don't be shy about asking your questions. And today we'll be discussing the topic of flexible machine learning systems. And we have with us two very special guests, Jeff Dean and Chris Ray. And they don't need any introduction, I'm sure, but I just want to share a little bit about their backgrounds to make sure we're all on the same page about just how awesome they are. Jeff Dean is the head of Google AI and the co-founder of Google Brain. He joined Google in 1999. His areas of interest include large-scale distributed systems, performance monitoring, applications of machine learning to search and related problems, and the development of new products that organize existing information in new and interesting ways, just to name a few. He received his PhD in computer science from the University of Washington. Chris Ray is an associate professor in the computer science department here at Stanford in the Info Lab. He is affiliated with the Statistical Machine Learning Group, the Pervasive Parallelism Lab, and the Stanford AI Lab. His work's goal is to enable users and developers to build applications that more deeply understand and exploit data. His work spans database theory, database systems, and machine learning. Chris was awarded a MacArthur Fellowship in 2015. He also received his PhD in computer science from the University of Washington. And I actually have a little bit of a personal connection to both of them. At Google, Jeff Dean is a legend, and so every employee gets a Jeff Dean number on their profile. And this indicates how far removed you are in terms of degrees of separation from Jeff Dean in the org chart. And I had a Jeff Dean number of 4 when I was working there as a PM. And as for Chris, I took Chris's CS 145 Intro to Databases class as an undergrad, and I can honestly say that he was one of the best computer science professors I've had at Stanford. So I'm very grateful to have both of them here with us today.
Thanks so much.
We're going to get started by having each of them provide an opening statement that introduces today's topic of flexible machine learning systems from their perspective. And Jeff Dean is going to go first, and then Chris Ray. And after they do their openings, then we'll open it up to all of you guys to ask your questions. And I'll also have some questions of my own to get the conversation started. So Jeff, want to take it?
Great, sure. So first, thank you all for having me. It's really exciting to be here, and I think on an International Women's Day, so happy International Women's Day. And this is an interesting format. Like I'm not quite sure what to expect, but here we go. I think what I would like to talk about is what I see in the field of machine learning today is we're having lots and lots of success at kind of finding interesting problems. Mostly what we're doing is supervised learning, and that can be extremely successful. We can actually collect the right data sets to do even fairly complicated end-to-end machine learning on complicated tasks. So if we want to learn to translate from English to Japanese, we can collect a big data set of parallel sentences, train a model, and those models are now doing better than any other approaches we know how to sort of apply for those kinds of problems. And every time we do even a small amount of kind of multitask learning where we say, oh, these 3 or 4 things are kind of related, maybe we should train a single model that does 3 or 4 things rather than just one, we tend to find that works pretty well. And we can do that either simultaneous multitask learning, or we can do transfer learning, where we start with a model for a related task, and then we sort of copy the parameters over and then fine tune on some other task, maybe where we don't have very much data. And so that usually works pretty well. But I think we're not nearly ambitious enough in this approach, right? Really, I feel like we should be training one model to do all the things we care about, right? Like at Google, we train thousands of machine learning models to do many, many different things. And each one of them requires, a lot of data, because they're all learning from starting random floating point numbers, basically, to try to learn to do new task. And of course, you need more data when you have no context about the world other than you were seeded by a random number generator with some random seed. I think there's a ton of interesting distributed systems problems in this. Obviously, the system, if it needs to learn to do thousands or millions of tasks, the hope would be the million and first task kind of comes along, and you can leverage the things you know how to do from the first million tasks to be able to get into a very good state for the million and first task very quickly and with very few examples. So that's sort of a direction I think the whole community should push. There's tons of distributed systems problems in there because you'd like the system to be very large in terms of computational capacity. You'd like it to be able to run even if parts of it are down and still be able to sort of make reasonable predictions or outputs even if this rack of machines is down. And there's also tons of interesting machine learning questions, because I think in order for this to be practical, it needs to be kind of a very sparsely activated model, so that for any particular task, you obviously don't want to activate an entire data center of chips for that task. You would like to find pathways through this model that are relevant for that task, but other parts are not activated when they're not relevant. So that's sort of a direction I think we should be looking, and I think will be pretty interesting. I'm pretty excited about it. It's a nice combination of machine learning research problems and sort of computer systems problems, and those are often fruitful and good for collaboration.
Awesome. Chris?
Yeah, so I think Jeff and I are really in alignment here. I think maybe the twist I would put on it is, in addition to the performance challenges and the systems challenges, I think also how people are going to build software is radically changing as a result of these massive multitask models. And to kind of understand that, I kind of give you a context of the things that I've been thinking about over the last couple of years. So 5-6 years ago, we were building these systems that were called joint inference and learning systems. These were systems that really had the hypothesis that if you could do many of these different tasks, 3, 4, 5 tasks at the same time, read a sentence, do some co-reference, understand a document, you could do something amazing or something higher than human accuracy. And we built some systems that could read scientific articles better than human accuracy, or we could fight human trafficking. We built a system to do that. We were kind of building these piecemeal things. Now, when we were looking through that, we realized that these systems were actually fairly difficult for people to code up, because what was going on when you were building these systems is that you would have some high-level mental model of the world of what the system needed to know, but actually taking that information and encoding it in a way that the machine learning system could do something useful and fruitful with it would take a PhD, basically, to sit down and do it. And a special kind of PhD who was willing to really get into the nuts and bolts of how these systems were constructed. So we did those things, and we were lucky enough to spin up a company and started to spend a little time in industry as a result of an acquisition. And what we noticed, actually, as we did this, was that actually most of where people were spending their time wasn't in constructing the models anymore. Great tools like TensorFlow and PyTorch and other things that were out there, they were actually taking fairly stock and vanilla architectures, deploying them, and then trying to figure out how to feed them with data and debug them and do all these different things on top of them. And so our first rev of what we were interested in thinking about then was trying to figure out, how do you feed all these different task heads like Jeff was talking about? How do we feed all the different pieces of data that it needs? And it was really about sample complexity that we started to build bigger and bigger multitask kinds of systems. But then something kind of strange happened. And the thing that kind of strange happened in both the open research and throughout industry, we've seen a couple of these examples, is that the way people approach their software engineering tasks seemed to pretty much change in some ways. They started to start from these kind of transfer learning baselines, or start from some of these tasks and tack things on. And we were having a little conversation before this started. You very often see this code that sort of lives with one team or lives with one task, and then all that knowledge is not transferred to the next task. And so there's a really exciting, I think, set of directions here to try and figure out how you unify a lot more of that information. And the other thing that we didn't expect, I think, when we started, but has been very nascent and early, is that these multitask systems, going back to those brittle ones, they have a richer vocabulary to talk to them. And developers seem to more naturally be able to go from those high-level expressions of, hey, it doesn't know about people, places, and things. Here's where I put it into the model. Or it doesn't know how to parse these particular sentences. That's where I should spend my effort. And figuring out where they spend their time seems to radically change how they build these machine learning models and allows them to build a little bit more flexibly. Now, that's really exciting, but back to the challenges, we have effectively no software tools. Somehow it feels like PyTorch and TensorFlow kind of came from the future and made our lives dramatically easier. And then everything on top is effectively feels like it's unsupported. There's just not a lot of computer science work that's told you how the classical system is supposed to work. How is this thing supposed to live over time? How are people supposed to share these models? And we just don't have a lot of research there. And I think it's a place where there'll be really fruitful research. The other bit that I'd mention is I also think performance is still going to be a really critical challenge over the next couple of years. And I hope that is something that, just to see the discussion, comes up in this very intimate salon with our 250 closest friends. This is a little different than I thought we were
more than
showing up to.
191. I think it's 191.
Oh yeah, it's 190. For legal purposes, it's 191. Yeah.
Awesome. Thank you so much for doing your opening statement. So now, if you guys have any questions, start raising your hand. Or if you're close to the edge, you can make your way to the microphone that we have right there.
So I've heard a lot. I heard you guys were both talking a lot about performance of ML systems. So I think that there's a lot of people at different levels of the software and hardware stack who are trying to improve the speed of ML systems, whether it's designing new chips like ASICs or FPGAs, or whether it's helping parallelize model training more efficiently and stuff. So what do you think in the next couple of years? Do you think we'll see a dramatic speed up in being able to train models comparable to how Moore's law was in the 1960s or 70s? What do you think?
I have some thoughts, but
Yeah. I mean, first, I think there will be improvements in many areas. I think ML hardware is different enough from sort of general purpose computer hardware that I don't think we have the full answer on what computer architectures will be most effective, and we'll get a lot of benefit from multiple generations down the road of sort of ML-focused hardware until we hit the kind of scaling limits that we've hit for general purpose CPUs that have caused them to plateau a bit. So I think we have several more generations to go of kind of Moore's law-like growth in the ML hardware space. I think that's one good thing. The second is the scale of systems may get larger even if the individual chips don't get faster. Well, both are happening, but the scale of systems will also go up, so that's a nice multiplicative factor in the amount of compute you can bring to bear on a single sort of problem or system. I also think some of these techniques algorithmically that sort of add sparsity to the model will actually allow us to train much larger models that have tremendous capacity, but because you're not activating the full model on every example, they're both faster for inference because you do less compute, but also faster for training because you now don't have interference because you're always updating every parameter in the model on every example. Instead, you have sort of different pieces, and that allows you to train these large capacity models more quickly. We've seen this in the outrageously large neural networks paper that I'm a co-author on, where we actually saw that we could improve the quality of the model by having lots of different experts, 2,000 experts, each of which has got 2 million parameters, 4 million parameters. And as a result of that, we're able to train in 1/10 the amount of training time and half the inference cost. And the system is higher quality. So that's usually you're trading those things off, but now all three are going up, so that's good.
yeah, so I think echoing many of the same sentiment, I think you are seeing sort of CPUs hit a plateau. You may be seeing GPUs starting to hit a plateau as well. And part of that is driven by current models and current architectures. A lot of what Jeff just described of how sparsity and more sort of data flow oriented processors coming along the lines could allow a couple of orders of magnitude improvement. It's not clear at all that if you want to do a big sparse computation, you want something that looks like a BLAS accelerator, a thing that does a gem block, a matrix multiply block, like you would get in a GPU or even in the old generation TPUs. This sort of more flexible kinds of architectures are things that I think will enable a huge number of these models and a huge number of multitask models. And they're going to be interesting because they're not, one of the things you've seen is that people will go and take their code and really specialize the heck out of it to try and get good performance on today's architectures. But when you start to do these more multitask models, you may no longer be able to do that. You may require a different degree of flexibility. And I should say, in the interest of full disclosure and academic purity, with Kunle, the father of multi-core here, we did spin up a company that is doing these more flexible styles of chips. It's called Samba Nova, and it's clear that there are big performance wins there. But these are radically different stacks that you can build. So I do think there are a couple of orders of magnitude that are hiding in there in performance, and I think that's going to change where people are spending their time in a pretty fundamental way. Just like GPUs did for machine learning. I mean, in deep learning a couple of years ago, when that switch happened, all of a sudden ideas that didn't work started working. I mean, it was awesome. And I think you'll see things like that happen. And multitask is one of my bets where I think that would happen. Maybe reinforcement learning would be another one, but it seems like it's ripe for that kind of innovation.
I'll add one more thing. I think building specialized hardware for a field like machine learning is actually pretty challenging because the field is moving extremely fast. And when you start a chip design today or a system design today, it kind of pops out the other end of that process 2 years from now, and then it needs to live for 3 years. So you're trying to predict what do we want to do in 2 to 5 years from now with the hardware we're going to start thinking about building today. And that's actually pretty challenging. So one of the meetings we have on a weekly basis that I go to is kind of a few computer architects, a few computer sort of software distributed systems people, and a few machine learning researchers coming together to talk about, where are trends in ML algorithms going, and where are trends in the hardware, what could we do in the hardware that might be interesting from an algorithms perspective, and vice versa. I think that kind of forum is really helpful to have these kinds of discussions about what should we be building 2 to 5 years from now.
And one program, if you're interested in following up, there's a program from DARPA that a bunch of us participate on that's this software-defined hardware. And the starting point of that project is we're not going to know what's going to happen in 2 to 3 years. Can we get something that is not an ASIC? An ASIC would be custom built for something. That's not a general purpose processor, but it's some kind of sweet spot, right? Architecture and systems always about those sweet spots. And those are interesting, bets to place of what kind of reconfigurability you can get and what kind of performance trade-off you can do. And the thing that's amazing to me is if you're a systems-minded or hardware-minded person, 4 or 5 years ago, it didn't feel like hardware was all that exciting. No offense to all my architecture friends. But now it's just an amazing playland because there's just a huge number of different designs that you can take. And you're seeing people rush in, big companies, obviously very famously making and offering pretty tremendous computing hardware. I thought that's something that surprised me. Google making its own chips. That was like awesome to me. Kind of opened up a field for a lot of people.
Here at Stanford, next quarter, we have a new quantum computing class, and one of the topics covered in that is quantum computing for machine learning. If quantum computing ever becomes a reality, would that have any implications to the types of systems that you're discussing right now?
It's possible. I think my view of quantum computing is it's going to be fairly narrowly focused on certain kinds of problems, and some kinds of problems are going to be dramatically affected. So if you're a cryptographer, you should be paying close attention. Mm-hmm. If you're trying to train, trillion parameter neural net models, it's not clear to me that the first generations of sort of usable quantum computers will be the first thing you should turn to. Mm-hmm. But you should definitely keep an eye on them. And I do think certain kinds of optimization problems are going to be pretty interesting.
I think Chris wants to say something.
Sure.
So you both sung the praises of multitask learning. So I want to push a little bit on that and ask, how strong are the results really? Because I kind of think multitask learning has worked great in some very closely related tasks. So, multi-language machine translation, yeah, that's great. And there seems like there have been a couple of tasks that have been very successful for transfer off. So, ImageNet trained vision models, they've worked pretty well. And these sort of contextual language models are pretty good to transfer off. But there's there's a broad range of tasks out there, and there are also a hell of a lot of negative results of people trying to do multitask learning. I mean, how far are we actually able to build these sort of many task models and get gains?
I get to fight with them all the time. Do you want to take this?
So I think you're right. There haven't been a huge number of like really strong results. You're starting to see ones in sort of very large language models being able to sort of tackle a pretty wide variety of NLP problems. We've seen this with vision transfer. I just think we have not yet pushed the scale of number of tasks that we really try to do enough to really know if you try to train a model to do, 10,000 or 100,000 tasks that are very multimodal, how can we learn representations that fuse together, visual representations of things, language representations of things, audio representations, and then allow us to hopefully take a new task and learn it with very few examples.
It's a bit of a leap of faith that if it doesn't work for 10, hopefully it'll work for 10,000, right?
Worked for deep learning. Anyway, but no, I'm just kidding. But no, being serious, I think when you look at these tasks, and to put even a sharper version on your question, the joint inference and learning, when the Bayesians were in charge, let's say, the problem there was that you would get these very minor gains, right? So when we would build these systems, you would produce your chart, and here's it where we do everything independently, and here we do a joint. And you had to squint, and you had to really stretch in. You had to have little zooms on your plots to try and show your beautiful benefits. And that was really depressing. I was building those systems, so I felt that depression firsthand. And so maybe this is just the same idea, but I think it's going to be different. No. So the reason it's going to be different to me and where we anchored on, actually, we're not the massive transfer. So there's a class of folks that are doing massive multitask learning, like Richard, for example, Richard Socher and other people like Deca NLP, the glue benchmarks and other things, where we would really love to have a wide range of transfer. And to me, this is important for pushing forward that more fundamental question, can you even do it? And the hypothesis of that work is, that's not trivial, and we haven't seen the gains yet. And basically everyone does tricks where they train these 4 tasks together, but not these 3, and they kind of get it to work. So I think that broad vision of you can throw in absolutely any task and it works, we're still a pretty good solid chunk away from. The place where I've anchored on it and seen it actually work and sort of demonstrate a value that I believe in and I think is worth doing is that's why I anchored more on the software engineering side, where you have tasks that are in industry which are different from academia in some ways, where you have many closely related tasks, where the models are not that different, where someone's working on one domain versus another domain. And there's a lot of information that very clearly transferred. An academic would look at this and say, these are the same tasks. But as we were talking about before, the different organizational units, they may be doing entirely different things. And there, it enables a level of code reuse that allows you to build these models dramatically, dramatically faster. And so I think those kind of software engineering wins I'm more confident in because I've gotten burned on the, hey, let's do the quality by itself a couple times. But there are places where it's starting to transfer, and maybe even more than we expected. Things like BERT and those kind of transfers are in some ways pretty spectacular and do, pre-training basically never worked until Elmo and those things, that line of research kind of kicked up again. So there is some hope for transfer in some of these richer and more interesting tasks. But it is an open question, right? And the last thing I'll say there is, it is true that the dream of all the tasks training at once, if anyone doubts that, go look at the Deca NLP, the way those systems are trained. They are trained with a block of tasks that work together and other tasks that interfere with one another. We have no idea why the interfering tasks are the interfering tasks. It's kind of all superstition at this point. So so you could look at that and say, oh, what do those jokers know? Or you could look at that and say, it's a tremendous opportunity for research. And as an eternal optimist, Chris, I fall in we look at it as a tremendous opportunity for research. But the point's well taken.
I'll add one more follow-up thought, which is unsupervised learning often hasn't shown to be very successful. But I think part of the issue is most of that work has tried to learn unsupervised representations and then do supervised training on the representations you've learned, rather than interleaving examples of supervised examples with every 1,000th unsupervised example you throw in a supervised example. And I think that could work better. I think if you start to have thousands of tasks you care about, and you have unsupervised algorithms that sort of can take advantage of the fact that I now know these supervised tasks, and these are the things I should be paying attention to in the unsupervised data that I have, because they're going to improve these 1,000 tasks rather than just this one task. That may be a way in which we can actually get unsupervised learning to work better than it has been shown to date. I don't have specific ideas about how to make that work, but I think there is promise there in saying these are the really important things to pick up on the data you're being exposed to.
One other thing I'll point out is even in your new benchmark, right, the sort of the visual, the grounded visual QA kinds of things, the places where we've seen the biggest bang for your buck in multitask learning, and some of the students who actually did the real work are in the audience, are when you are combining vision and language. You know, we've been doing it primarily on the medical side, but there you do get a very non-trivial lift from doing them separately versus doing them independently. But again, still early days, and I love the vision of doing absolutely thousands of tasks together. We're sort of at tens of tasks now, and still kind of praying it works. But yeah, it's a really interesting point. But that's your benchmark, so it kind of works okay there. So, yeah.
Let's get you in the white sweater. Sure.
Cool.
Thank you. So Jeff, a lot of the questions that you asked reminded me of the human brain and human cognition. It sounds like you're trying to turn Google into a giant brain, which is a great idea. In human wetware, one of the powerful mechanisms we have for dealing with unfamiliar circumstances is associative recall. When I present my brain with novel information that it doesn't know about, it fetches something for me. It may be based on auditory similarity, visual similarity, semantic similarity. There's some fundamental associative mechanism which we don't currently have in the machine learning arsenal. So my question is, if we want general purpose machine learning and aspire to human level intelligence, don't we need to solve the problem of associative memory?
I agree with the premise that when you are exposed to data, you want to be able to find similar things and understand how, you know, past behaviors and experiences have in those other similar things might help you in solving this new situation or task or example. I think one of the ways you can do that is have models with enormous capacity so that you can be exposed to very large amounts of data and then be able to recall the sort of relevant pieces of it that are similar to something new you've seen or heard or read.
I don't think we have any associative algorithms that resemble human performance. They're able to recall things just on arbitrary similarity.
Well, I think a lot of the representations that some neural net kinds of models are learning actually are, when you have similar sort of high-level activations, those experiences are actually similar and to other ones that a system has been exposed to.
Was that a result of training?
Yes.
Okay, so I'm talking about the case where there's no training. I
Well,
presented the first time.
what do you mean by
information, I
no
come up with
training?
So I encounter information every day that I haven't been trained on, yet my brain is able to respond and present me with relevant information. There was no supervised learning that took place.
Well, there was before. Like you had all this, you know, lifetime of experience, both unsupervised and supervised. And that, I believe, helps you in trying to find what are the relevant pieces of information or similar kinds of experiences that will help me in the current context.
Okay, I won't argue with that.
Anyone else? Back there, a few rows down. Can you pass the mic?
So we're talking about like understanding things flexibly. Whenever I see an adversarial example, I always wonder like how much is this some leak in a pipe that we can fix? Like, you know, we can just make our statistical system more robust to it, and how much does it show that? Like, how much does it makes me question like how much did this algorithm really learn in the first place? Like, it seems like if I show a human how to classify this animal, there's no way you're gonna inject some weird noise and get a human not to classify it. And so I'm curious, when you see adversarial examples, what that makes you think about in terms of learning, and if any, specifically what you've talked about, like with flexible learning and trying to learn across different tasks, if you think that relates to these sorts of adversarial examples.
Sure. So I think, you know, the adversarial examples are fascinating and they're fun to work on. And there's a bunch of folks who have been thinking about sort of the properties and problems really deeply. But I think sometimes we get ourselves a little bit too humanized and fooled about the adversarial examples. There was a great Google paper that I loved that was basically showing images to folks that were resource constrained. So they would show them very quickly. And they showed that they could actually fool people in that kind of resource constrained environment, similar to how they were fooling models in kind of similar ways. So while it's sometimes like disturbing that you find these adversarial examples, I mean, you can create them for linear models too. I never really, this is a personal take, got why it was so disturbing for the deep models that you would have these boundary conditions where they were less smooth. It's L-infinity regularization. You just want to make the landscape smooth. So the fact that those examples exist that are like small perturbations that change it in a complex landscape, like that's kind of always going to be there in high dimensions. So it doesn't make me question the fundamental tenets, but it does provide a really interesting way to think through these problems. I mean, Percy's work in this area I really like. John has a bunch of really cool work as well, where they're trying to think about how to actually certify that you're robust to certain types of perturbations and understanding what those perturbations are. You change the model, what's actually going to happen? And so I think it's going to drive a bunch of these things, but it's not clear to me that multitask learning makes it any better or any worse. It's an interesting direction to think about. I haven't thought about multitask adversarial examples before, so that's super cool.
So I would just add, humans are not as fooled by adversarial examples because we have 18 years or more of training of our visual system, right? And I think when you think about a system that is trained on ImageNet, it's been exposed to a million JPEG photos, right? That's nowhere near as powerful as 18 years of experience. And I think the paper that Chris mentioned, when you have very short amounts of time to look at things, that paper showed that you can basically be fooled into thinking something that is a cat is actually a dog. But if you're given more time to think about it, you're like, oh, let me look at it again and kind of take this hypothesis and evaluate what that hypothesis might mean if I looked at it this way. I think that's what's happening sort of beyond the initial glance that your visual system is taking. And I think we need models that are much more about proposing a bunch of plausible interpretations of the data they're exposed to, and then can evaluate the consequences of those different hypotheses and explore the space of possible hypotheses in order to actually come to a conclusion about what this means or what action makes sense and that kind of thing. And I think if we have that, we'll be much more robust to these kinds of examples or problems like that.
One of the key issues for regulation, ethics, policy is the interpretability of the models. Do you think that if we go towards more flexible multitask models, could this lead to making them harder to interpret, easier to interpret, or it's not necessarily correlated with that?
Could be either way, I think. I think we've done, the research field as a whole has made some progress on making models more interpretable in the last 4 or 5 years. Things like attention mechanisms or in visual systems being able to view based on sort of gradients and other kinds of visualization techniques has helped somewhat. I think ultimately for interpretability, you want a system that you can have a dialogue with about, okay, you think this, what makes you think that? And then you can get into a bit more detail about, why that particular part of the evidence, is what is believed to be this way. Sort of the way if I ask Chris, well, why do you think, they painted the room this color? You can then tell me. You have no idea. Do you think maybe it's because it's light and bright and
That sounds reasonable.
Yeah.
Yeah, there we go. We got to the bottom of it.
So I think when you have humans are not actually all that interpretable, but they do have this property that you can ask them questions, and eventually they kind of bottom out and I just felt like that was better than that.
I trust Jeff. That was the end thing. But yeah, so I think, getting to this question of interpretability, that's a really interesting and fascinating question. And regulation is something that I think, I'm glad it's on people's minds, right? Like these things are getting deployed. There's a lot of people thinking about them. There's this great AI safety group at Stanford that's really thinking about these questions deeply. And I'm really excited about that. My guess is that I don't see why this would make this a more difficult problem if you have these more flexible systems. When I've seen people go through the debugging loop and try and understand how they're going to correct those errors, as I talked about this richer vocabulary, being able to check their understanding that, oh, I understand that it got all the parts of speech. I understand it got the typing right. I understand it knew what the question kind of meant in some vague, sort of sense. I can check all those things, and it gives me a much quicker specification. When you're having a conversation, it's the same way you can check that it's in the same frame of reference, that there's not some kind of missing element. So the more the model produces, it seems like the more information it reveals, and the easier it makes it to hone on those conversations. Now, are there strange things lurking in there? Are there adversarial examples that attack this multitask thing? I have no idea, but that sounds awesome. Like someone should look into it. But yeah, I have no idea how people are going to actually regulate these things effectively, except through the methods that Jeff is talking about, where there's sort of, you're certifying from the outside that it meets some operating kinds of characteristics. Right? Another thing where stochastic gradient descent effectively runs are like controllers, right? Controllers are basically doing the same thing. We certify that planes are going to work okay, and we're happy to fly around in them. So maybe we can develop similar kinds of certifications, and I think that's a potentially promising direction.
You in the middle?
So these higher-level libraries like PyTorch and TensorFlow have had, I think, objectively just an outsized influence on the machine learning progress in the past few years. Just really brought higher-level ideas to the masses that they can quickly explore these things. So from your standpoints as heads of organizations that have a mandate to look way in the future, what do you imagine the TensorFlow 5.0 looking like, or whatever replaces it? I mean, what will the interface to building these models look like, in your opinion, in some years from now?
Yeah, I mean, it's hard to know. I think there are interesting software engineering questions around if we're trying to train a model that does many things. Presumably you're going to want many people to collaborate on building that system rather than what we have today, which is like a handful of people work on one model and they're sort of largely isolated from decisions made by other people. I think I was actually having an interesting question of whether ML systems are more like programming languages, which tend to change fashion every 10 years, or are they more like scripting languages, which change fashion maybe every 2 or 3 years? And it seems like they're more like the latter, right? Like people tend to, because the field is moving so quickly, people develop new abstractions relatively fast and new ways of expressing things, and I think ultimately we'll end up with a bunch of software infrastructure and then perhaps many different ways of expressing different kinds of computations that shares the same sort of compilation infrastructure that can then map that the kinds of compute that we want to apply for ML algorithms onto many different kinds of hardware. But I don't quite know what TensorFlow 5 will look like. But.
Do you know when we can download it? Yeah.
There's an early release of 2.
Yeah, 5.0. Yeah. So I think it's a great question.
Keep reloading.
So I think it's an interesting question. I mean, to my mind, there's kind of 2 big splits that are going to come up. One is around, how do you take, and Jeff made a bunch of great points about collaborate on these models, manage these models, put them into production and monitor them, and that's going to cause a growth of software tools that is clearly missing. The kind of APM framework for machine learning just doesn't really exist right now, and that will clearly, as more people run it, that's going to start to happen, and I think that will drive a lot of the software development. The thing that's less clear to me is what happens to all of machine learning. Like TensorFlow and PyTorch work great and do a huge swath of what's available today. But there are a couple of things that sort of sit on the outside, and I don't know if they're going to be absorbed. Reinforcement learning, there are great frameworks that are going on there. Will that spike off into its own area? Writing a reward function is a hard and challenging task. Is there an entirely different software abstraction for that? Seems like there could be. Seems like you may want different tools in that kind of thing. If you go to more observational kinds of models about the universe, where you're trying to learn from video to do another task, is it clear that these are the abstractions that you actually want to wire it up? Is it so low level? Is it something that looks more like Keras? Is it something that's much higher level entirely? If AutoML starts to work at a much larger scale, which these guys are burning lots of TPUs on, and what is it? Data points and papers that cost $1 million. It's amazing. If you imagine that you're able to search over a lot of this, does that obviate the need for this infrastructure? maybe TensorFlow becomes like your assembler, right? Like it's there, it's a spec, it's something that you want, but you have much, much higher level interfaces. I think that those big rapid productivity gains are more possible for AI than they were for sort of traditional software. Again, maybe that's just hopeless, crazy optimism. But I think that's why it's hard to answer what's in 5. I think it's hard to answer what's in 2, at least from my perspective. Yeah.
I mean, I think one good abstraction that we do have is, here's a supervised learning task I care about,
Yeah.
right? Don't specify anything else. And the system figures out, how can I make this supervised learning task work well in the context of some large system, right? So I'm imagining in this large multitask system, that may be the way you specify a new task. And if we're routing around examples based on sort of some representation of the task or some representation of the example or some combination of those, what you're going to want is different pieces of the model to be able to adapt to different kinds of data. Like this part is kind of good with visually things, and this one's good with this particular kind of language data. And each part of that may be running its own kind of little architectural search to adapt to the stream of data that it's being sent. And then you're simultaneously learning to route through this model to figure out which parts of it are really good at this particular thing you care about. And so I think by sort of combining ideas of neural architecture search or other kinds of AutoML and kind of these sparse expert-like models, that may be a pretty interesting direction to go in.
And one little shout out to work that I really like is this new system, Ludwig from Uber, which is like super cool, very declarative, and they're moving from this idea of specifying the architecture to many more higher level things. Just give me basic adapters for types and stitch them together. And the reason I think that's so interesting is just like you had differentiation in what kind of programming tools people use, the power users versus kind of scripters versus Excel and all the way on down. There's no reason that I think if these things are as pervasive as I personally hope that they are, that they don't differentiate in those ways. Maybe you don't have the best image model under there, and you're not willing to spend the budget to get the neural architecture search to refine it, but you can get your immediate task done and decide if you want to do with it later. So it's not clear to me that back to the is it a programming language, is it a scripting language? It's not clear to me that it's either if it's not going to fragment into kind of radically different camps that are able to do each of these. I don't know why it would be so monolithic. That hasn't happened previously in computer science to my mind.
In some of the papers that you shared, the learned architecture from neural architecture search actually outperformed the human engineered architecture. Do you envision a future in which the entire architecture or the entire system is itself, so an AI system itself is designed entirely by AI, or do you think that we actually need the human engineers to set parameters to ensure that this is something that we can interpret and manipulate as we see fit?
I think the work that has happened so far in these kind of meta-learning approaches really requires human expertise to craft the search space in such a way that it is big enough to have interesting parts of it, but small enough to be practically searchable. So that means like 10 to the 30th, not 10 to the 60th. Mm-hmm. And there's actually a real lot of art in getting a search space that is that just right sized thing. But I think the benefits of this kind of approach are, machines are much better at running repeated experiments and learning from the observations of the previous 50 experiments, or at least they're much faster at it, and deciding based on those 50 what are the next 50 experiments you want to run. If you can define the problem as sort of an RL or an evolutionary style algorithm, then the system can run 20,000 experiments in a few days, and it's pretty hard even for the best graduate students to do that. Particularly if it's many cycles of 50.
All the way in the back.
Topic of study, but it's been studied since the early 1900s. Psychologists have been looking at it for a long time, both in educational psychology and in cognitive psychology, and there's good theories of transfer in humans. And there's been computational models that fit the data very well, and the basic theory is that expertise comprises of a set of knowledge elements. That different tasks depend on those different knowledge elements. And that what's going on in transfer is you learn on one task, you have to master those knowledge elements, and then you come to a new task that may have some overlap, and now you only have to learn the new ones, right? And that gives you a very straightforward way of dealing with constrained inference, because you only want to access the knowledge elements that are relevant. Now, the computational models of transfer and human learning have mostly been either rule-based, where that's what the knowledge elements are, or say structural analogy, right? Sort of case-based with rich representation. But it doesn't have to be that. There's nothing about neural nets that say that you couldn't play the same game where you have parts of the net that are relevant enough for some tasks and not others. Although that's not how people talk about it, and I don't hear you guys talking about it. Well, okay, but the language is certainly not coming out. And I just want to make sure that we don't, in the excitement about the new generation of learning methods, that we don't lose sight of those core ideas, because they're really powerful, and that we continue to look at the old results and to say, okay, well, how can we get the same kind of thing in this new framework to get the same effect? So I'm glad to hear you say that you are thinking that way. Could you rephrase what you said earlier in those terms?
Sure. Let me summarize. I'm not at all familiar with the psychology literature and human transfer learning.
I'll send you some links.
Sure, that'd be great. But my intuition about when I need to learn to do something new is I look at this new thing, I'm like, oh, I know how to do these pieces of it because they're very similar to other things I've done. And then there's like this couple of things I need to figure out that are new, and I might need to experiment, or I might need to sort of try a bunch of approaches, and then sort of collectively I put all that together, and now I can do a new thing.
Elements in the neural network.
So the knowledge elements in the neural network are that you're going to have different pieces of expertise, different centers of expertise that allow you to have these pathways through a large model for different tasks. And
you're saying in principle, you could, for this task, you could have a subnetwork, and for another task, you have a different subnetwork.
Yes.
And over time, you want to build it all.
Yeah.
That's great. I didn't hear you say that, and
Sorry.
I'm glad we're on the same page.
I will say it a little bit more clearly. So there's a couple of pieces of work that we've done in our research group that I think, if you put them together, get us more in this direction. So one is this sparsely gated mixture of experts work, where basically you have a traditional neural net, and you can graft in the middle of it something that now has thousands of experts, 2,000 different experts, which you can think of as their own little miniature neural networks, and a learned routing function that learns, for this particular example, this expert is really good at that. And for this example, a different expert is really good at that. And occasionally you send it to 2 experts, and that gives you a gradient signal to train the gating function so that it learns to route to the better kind of thing. And you actually see in language models or translation models, these experts do develop different kinds of expertise about different kinds of language. This expert is really good when the context is talking about dates or times, and this one's really good about sort of biology and biotechnology related language and this kind of thing. In that initial work, all those neural nets had exactly the same structure and didn't change their structure. In neural architecture search, a completely different project, basically models can evolve structure based on the problem they're trying to solve so that they can find accurate model structures that work well for that. So now imagine each expert running its own little architecture search, and we're routing not just examples from the same task, but many different kinds of examples from potentially many different tasks, so that we now have an expert that learns to do similar kinds of tasks or similar kinds of contexts.
So I do want to make one comment there. So 2 pieces of work that I think are interesting and relevant. One is there is actually, and those are great pointers, and definitely please send them along. There is a bunch of work. I think some of it was done actually, the initial work was done at DeepMind, where they were trying to actually very explicitly figure out those modularity boundaries of this is a task, and once you've learned it and mastered it, now you can move on to the next bit of the task. Almost verbatim to your description earlier of, I've mastered these first 4 things, and now the 5th element, which do I use? I may only have to use 2 of them. How can I deduce that and do it? And they were admittedly sort of toy problems, but I found that particular line of work fascinating, and maybe even unaware that their motivation probably came came almost directly out of what you described. The other bit that I would say is when you think about, when I was describing how these systems, these multitask systems are built and deployed, they really follow a model that's happening on the engineer side. It's not yet happening inside the model itself, but there are tasks that are accomplished that now we know how to do this. We know how to understand some piece of the text. We understand how to do some typing task. And we want to combine those. And that's right now, and at least the approaches I've seen, left to the expert coder to say, let me select the model that the task that does the typing. Let me select the task that does the part of speech recognizer. Let me suggest the part that knows about sports or music or whatever it is, or biotechnology, and I'll stitch those together. It's very exciting to then combine this with what Jeff is describing. But that lack of modularity, I think, bothers a lot of computer scientists on sort of first principles, that if we put everything together and just sort of learn everything from scratch, it seems like we're leaving out what has been, at least in our own experience, one of the most powerful forms of learning. And I think people are working on it. We just kind of don't know how to make it work right now. And maybe these pointers are the way there.
Along those lines, I think we have techniques where we can take a very large model and transfer it to a much more computationally efficient model. Things like distillation allow us to basically use that large model as a teacher for a smaller model. And because you get this really rich gradient from the large model, that enables you to get like thousands of bits of information flowing as gradients for the small model. And so with a small number of parameters, you can actually get much more accurate small models than you would just by supervised training of the small model itself. I think in this very large system, you're going to need some sort of meta-level controller that makes decisions about where does it make sense to add capacity to the model, and where does it make sense to sort of slow down learning because it doesn't really seem to be changing very much in this part of the model. And distillation may be a technique whereby you can effectively take some bigger part of the model, distill it, and now you've freed up some memory that you can now use to add capacity in some other way.
Black jacket.
I actually have a question for both Jeff and Chris. So basically, in terms of deploying machine learning models, there has been a lot of efforts and successful stories in doing inference on edge devices like smartphones, like smart homes. But there seems to be less effort, or is still in an earlier stage for training on the edges. So basically, from your perspective and experience, what is the strongest incentive or the most useful applications for training on edge devices, and what are most significant obstacles you guys are thinking? And do you think it is the right time for it to flourish, or it is like 20 years ago for autonomous driving?
So I think you're getting at some of the things that Google and other folks coming out of our lab, like Virginia Smith, who's now a professor at CMU, work a lot on the federated learning side of the world that are trying to train them. By and large, those results, at least as I understand the bevy of them, don't do it for performance reasons. They do it for other reasons motivated by privacy. In fact, they may send many more amounts of data back, but it's motivated by a higher level concern. I think that is unquestionably happening already today. I think the question of how far you can push that, what algorithms are there, what kind of pooling you can do, I think those are really ripe and exciting research areas. I don't know what you think.
Yeah, the other thing is I think, certainly for privacy reasons, doing things like federated learning make a lot of sense. In fact, we just open sourced, like yesterday or the day before, a bunch of tools that enable us to, other people to use the same federated learning systems that we're using internally. We use that, for example, to learn Android keyboard models where we obviously can't send the keystrokes people are doing to a centralized location to train a model, but you still want a nice predictive experience when you type the first part of a word to have that complete in reasonable ways. And federated learning is a really good approach for that. I think the edge systems capacities at the moment are much lower than data center systems you can build. And in terms of training resources, even if you have a lot of phones, it's hard to really add them together because the bisection bandwidth you get from edge training there. I do think there may be opportunities to do kind of adaptation where you do a little bit of training on the edge to adapt to your current context. To date, people haven't done very much of that, but that may be a place, especially as edge devices get more and more ML accelerators in them. In the next few years, high-end phones and medium-end phones are going to all have ML accelerators of some flavor or other. And so that'll give more compute for these kinds of things.
Here. And then I can also do a second question as well so that we can get it going. So who's anyone else? Okay, and then we'll go there afterwards.
Here's neighbor.
A bit about something you guys mentioned earlier in the talk. So you talked about like the difficulties of creating like specialized hardware for machine learning tasks because what people are doing changes so quickly and there's like a 2-year product cycle. So the question I wanted to ask was what do you think are like the opportunities to build software to actually improve ML training and inference? So one thing you mentioned was like training sparsely. That's an example. Like another thing that comes to mind is like asynchronous gradient updates or like relaxing like certain things like that exist in computers like cache coherency and stuff like that to basically like accelerate the task of training and also or like on a different flavor like maybe having some kind of domain specific language that like speaks closer to the hardware basically general question is like what type of software improvements do you think there's like opportunity to improve on that don't necessarily need improvements in hardware?
I mean, I think the biggest promise is in new kinds of training algorithms or optimization algorithms that sort of could radically speed up the way in which we sort of collectively train a model to high accuracy. If we're able to do that, second order methods like KFAC or something like that are promising things. I think, they haven't to date had a huge influence, but they may in the future, and I think people are looking and understanding the sort of more theoretical aspects of optimizing these incredibly high-dimensional non-convex functions. And so it's possible that we may make a lot of progress by coming up with better algorithms for optimization or completely radically different kinds of machine learning models that are trained in a completely different way. That seems possible and might give you, factors of 10 or 100, but it's hard to predict these sorts of things.
Yeah, so I guess two things. So we did a bunch of the early work on the asynchronous stuff, and then by and large, where it's had people using it, or like NVIDIA did a very nice thing where they showed that by basically delaying updates, they could communicate 1,000-fold less frequently, and by correcting the algorithm. It's called the momentum correction, which was done by a postdoc, Giannis of mine, who's now at Mila, one of the Canadian deep learning institutes. And so that stuff, there are these opportunities to kind of tweak an algorithm and make it responsible for all the way down the hardware stack. And that's a super exciting that's a super exciting line of work that's going on. When you start to look at the, why don't we apply higher order methods and second order methods? And, a lot of folks have done various different second order methods on these things, and they by and large haven't caught on. They were the, standard before, and then they haven't caught on. And part of that's because we don't really understand the loss surfaces of how these functions behave well enough to really make approximations. Like everyone's kind of doing, we did a bunch of stuff on low precision and training on compressed models, and those things give you orders of magnitude today in various different regimes. Like the best number on ImageNet right now, picked up on one of our papers that did low precision, mixed precision training, which is this ImageNet in minutes paper. They use some of those tricks to, get to the very limit. So there's a lot you can do in software, but it's really hard. It really takes a full stack optimization approach to go all the way from the software all the way down, and they can be a little bit brittle when you use them. And so there's a kind of a question underlying of robustness. Now, one thing that I want to plug, and this will show my true colors as a theory nerd, is there have been a bunch of recent papers that are describing what stochastic gradient descent is actually doing on a lot of these ResNet models. There's a Jason Lee's paper in particular is one that we were just reading in reading group. There's a collection of 5 or 10 of them. And there is kind of an emerging theoretical picture of, even though these functions are non-convex, hey, they may be producing these things that look like really big random features kernels, if that makes any sense. The important part is there may actually be some theoretical understanding of what these algorithms are doing, right? So the tack that we've been taking is, we know there's a trajectory that's good. Can we modify the algorithm to go, just as fast and kind of match that trajectory? And some of these results aren't saying, it's going to converge under any situation, but these results are super, super exciting because they suggest that it's possible to really dramatically compress a machine learning side. So I think, sometimes in deep learning, because the successes have been so heavily weighted on the empirical side, that some of the older optimization and kind of more classical theoretical things have kind of fallen behind the empirical, like, let's run it and do it and see what happens. But I think there's going to be a little bit of a swing to theory, and that may be a prerequisite to unlock the next version of these software things. So I'm very bullish on what's going to happen on the pure software side and compressed low memory training over the next couple of years, just based on these recent results.
Let me touch on asynchrony, because I think that's pretty interesting. When we first started doing a lot of work on neural nets at Google, we actually didn't have accelerators deployed in our data center. We had just lots and lots of computers. And in order to make that practical so that we could train very large models at scale, we actually developed and used a bunch of asynchronous techniques. So lots of replicas with a centralized parameter server, and kind of the gradients were all stale and flying around. And that actually works. But it's hard to understand, right? Because in this big distributed system, gradients get delayed, and it's not always repeatable because every run is somewhat different. And so we moved to really large-scale accelerator-based supercomputers that have really high-speed networks and allow us to essentially scale using synchronous training. And that's much more understandable from an algorithm standpoint. You already have enough trouble understanding what's going on in your ML model if you don't throw in asynchrony as well. And so that's great when you can use synchronous methods. I think some of the models we're going to want to train, though, are at a scale where we're going to have to go back to asynchronous methods. Like the system I'm describing with these many different experts and so on, I think is going to be such a large scale that it's not going to be possible to do it completely synchronously. You're going to want kind of millions of examples flying around the system in various ways and continue updating bits and pieces of it sort of asynchronously.
So one bit there too is there are many levels you can play that game of being asynchronous. The point of those papers, the Hog Wild paper and the other papers that came after it, were basically to say like, oh my God, this doesn't look like a classical system, right? They weren't saying this is a great idea, okay? I don't think I ever wrote that in the paper. I just said like, this is interesting and it works sometimes, and oh my God, it turned out people are using it, which was a big surprise, okay? We didn't name it Hog Wild because we thought people were gonna use it, right? But being serious, the underlying results that are there that sort of tell us that we can understand how these trajectories are modified, that's kind of interesting, that the changes in the algorithm modify the changes in what you can do on the hardware. And when we did some stuff with the labs a while back, the national labs, and you wanted to scale up at the time to, I think it was 15 or 50 petaflops. I forget the number that was on the paper with the Intel folks. But when you did that, you were synchronous up until you could be, because why the hell wouldn't you be? If you could go synchronous and understand what was going on, and there was a little bit of asynchrony at the end. That's one way you can play it. You can also play it really in the guts of the algorithms and the way the hardware is built and designed. And that may be another place where it's a little bit more manageable. It's not gradients that are getting delayed by an hour. It's gradients that are getting delayed by 2 clock cycles. And that we do have a little bit of a theoretical understanding for. I think the interesting thing about all that line of work isn't necessarily that it's a good idea, but it is that there's a radically different set of trade-offs that you could potentially open on these systems that are just amazing. You can compress them in ways that are just freakish, and they still do the right thing. And these are just tools to try and understand that. So I think the software innovation side over the next couple of years is still going to continue to be where a lot of action is. The hardware side of this is because it's very clear that you are hitting some of these limits, and whenever your hardware can go faster, like everybody goes faster automatically, right? So if there's faster hardware, like people are going to use it, and so that's why there's so much innovation over there.
We're close to time, so let's do this question quickly, and then we can move to our closing comments.
Push further on this multitask idea on like robotic task. We know there are 2 types of robotic tasks. One is like
hold your microphone a little.
Where you play games and you have infinite amount of data, you can train fancy RL algorithms. There are also like real robots where you don't have like huge amount of data and you need to rely on the more traditional perception plus control approach nowadays. So do you see this multitask framework that is mentioned here being useful for this robotic task to leverage all those like simulator experience to gain like kind of game level robots in real world?
Yes, absolutely. I mean, I think our robotics research group is looking at a lot of different kinds of thrusts of robotics research. So one is actual physical robots that can learn from self-experience. And in particular, when you have many of those robots, they can pool their experience, and you can train models so that you learn on more than just a single robot's experience, but collectively you get 20 robots doing things, and they're all subtly different. You actually then can learn things that are a bit more general than exactly that robot's particular joint tightness or whatever. And then we're also doing a lot of work on transferring simulated results to real robots and learning sort of how to actually take the simulator, which is a not perfectly faithful representation of the real world physics, and make that work. We're learning from demonstrations. So humans can, for example, give us 5 or 6 short video clips of humans pouring into different kinds of cups and mugs, and then the robot can use those video clips as input and then also do some reinforcement learning. And with about 15 trials and 15 minutes of experience, it can actually learn to pour kind of at the 4-year-old human level, not the 8-year-old human level. And so that's kind of encouraging. And I think all these things, you're going to want the ability to have a whole bunch of robotic primitives, like pick this up, move it over there, put this in there, that you can then stitch together to build more complex robotic actions. And that sounds like a system where heavily multitask learning and these kinds of perhaps even learning to put together simpler tasks into more complex tasks is something that you'll want to be able to do in robotics and many other things too.
Great, and if you have any last thoughts on this topic, and maybe if you can include in that, what would be like 1 or 2 high impact problems that people could focus on if they want to make a difference in moving us toward these more flexible ML systems?
Yeah, so first, thank you all for coming, and Jorge and others for setting this up. I think this was a lot of fun, and I didn't know what to expect, but this was pretty cool. In terms of what would be the next generation of these kinds of systems, I think the directions you're talking about of moving demonstrations and simulators across is a really interesting area for these multitask systems. The one that I keep saying in my lab, and I think all my students think I'm joking, is that I want to be able to watch NFL films and play Madden. This is a dream of mine to be able to do this, and I think we're a couple of years away from doing it because it requires being able to automatically craft reward functions and move across and use some IRL-style techniques and do a bunch of things that are there. I think the next generation of these systems are going to come from these much richer environments. I think what's happening inside academia, that was happening that is not happening any longer in academia, is people were focusing on the single supervised case and single supervised benchmark. Now you see these great things like glue, you see these things like DEC NLP that are forcing you to actually contend with reasoning in a greater extent in the real world. And I think that is some place where there's going to be a lot of really, really exciting progress. Glue is just a super interesting thing, although my students are grumbling about me making them do it right now. But I think it's a super cool thing. So I think thankfully you're seeing NLP and vision and other areas start to say, bring all the data together and force it to really do something exciting. The grounded reasoning is in that vein as well.
I think your Madden example would be even more impressive if you went the other direction.
Actually play in the NFL? Yeah. That's a good idea.
I think one of the things about if we do push in this really heavily multitask direction, there are tons and tons of really interesting machine learning research questions, distributed systems questions, software engineering questions, how do we specify such a system? How do we have lots of people work on it together? How do we, solve some of the interesting problems like, how do we learn to route through this large sea of components? How do we add new components? How do we add capacity in the model where it makes sense, remove capacity where we're no longer needing that? How do we sort of take on a new task? How do we stitch together maybe some of the kinds of individual things we already know how to do into more complex kinds of programs or algorithms for solving a more complex task? I think being able to do those kinds of things seems like what we really want, which is to be able to take a new task, and be able to have a system solve it either automatically or with a little bit of human guidance in order to tackle new problems.
Thank you. So in this discussion, we've identified lots of opportunities and also some challenges across software, hardware, theory, and as students, we're in a great position to be able to take these ideas and infuse them into the work that we're doing on a day-to-day basis. And I know there's also a lot of visiting PhD students, so hopefully that'll get you thinking on the type of research that you could do once you start your PhD program. So I really want to thank Jeff Dean and Chris Ray for spending their time with us today and contributing to this discussion, and to thank all of you guys for coming over and also sharing your thoughts and your questions. And thank you as well to all of the staff and the faculty who came together to make this event possible, and I hope you guys enjoyed it as much as I did. Thank you. We would also love to get your feedback, and we have a bit.ly link set up, bit.ly/AI Salon. So please log in and give your feedback. Thank you.